So this is Advanced Higher Chemistry, and we are working on Unit 1. We're working on the first half of Unit 1, Inorganic Chemistry, and this is our second lesson on electromagnetic radiation and atomic spectroscopy. So in the previous lesson, you learned about electromagnetic radiation, and you were looking at working out the energy associated with photons of light interacting with chemicals. And you're probably asking yourself, what's this got to do with chemistry? Well, whenever photons are emitted, given out, or absorbed by atoms, this energy is given or taken away from electrons. And electrons are responsible for all chemical reactions. If an atom is given energy in the form of heat or light, electrons can be promoted to higher energy levels. So that means they move from one shell to a further out shell. We describe atoms and electrons that have moved to higher energy levels as being excited. And when those excited electrons move from higher back down to lower energy levels, they release photons. So a good representation is on this diagram. So this is sort of a half of an atom shown, and we can see we've got one electron in the first energy shell or energy level, the nucleus at the center. Whenever a photon is absorbed, that photon gives energy to the electron, and that electron, you can see it moved up to a higher energy level. Now we've got an electron in the higher energy level. If we no longer have light or heat keeping it in that energy level, it'll fall back down. Now it doesn't have to fall back down to the exact same level it was in before, it just needs to fall down a bit lower. And when it falls down, what happens is that it emits a photon. Now each element does this process differently. The energy of those photons means that they appear at different wavelengths and different frequencies, and different wavelengths of light show us different colors. So we've got 5 elements here, and everywhere you see a bright light, that is the wavelength corresponding to an energy change in energy shells for that element. So you can see that hydrogen has hardly any lines. Then next we have helium and lithium, and you can see that oxygen, which is the heaviest, the most electrons of all the elements on that page, has the most complicated set of lines, and that the lines occur at different colors. So why does this happen? And why is each element different? Well, it's because each element has its own set of energy levels, and excited electrons are falling to these different energy levels. Each specific transition, so from energy level 3 to energy level 2, or energy level 3 to energy level 1, etc. Each specific transition will emit one specific photon. So that means that photon has a specific amount of energy and therefore has a specific wavelength. And wavelengths are different colors. Now the fact you have different bands, different lines, it means that there are different and discrete energy levels in atoms. By discrete, we mean that they are fixed energy levels, and that from one atom to the next, the values of these energy levels are different. And we describe the energy levels, or energy electron shells, as being quantized, meaning that they have a very specific and measurable amount of energy. Now, this principle is the reason why metal ions give out different colors in flame tests. Whenever you heat up a metal ion, what you're doing is you're giving the electrons energy, and they are becoming excited and move to higher energy levels. As those electrons fall back down to lower energy levels, they release photons of light. Those photons of light give off different colors depending on the energy difference between the higher and lower energy levels. And for every type of metal, that energy difference is going to be different, and it's going to happen at a different wavelength of light corresponding to a different color. So that's why you can use the different colors to classify and identify the different metals used in a flame test. So we're going to look specifically at hydrogen. Hydrogen only has one electron, but we see several lines. We don't just see one line for this one electron, which might seem strange. And the reason for that is because the electron can move between several energy levels. And so every time it makes a transition, you get a different line. The difference in energy between the levels can be calculated by looking at the wavelength or frequency of the light coming from an emission spectrum. So here we have just a representation. We've got the third energy level, the second energy level, and the first energy level. The part of the electromagnetic spectrum where the lines show up is dependent upon the energy level to which the excited electron falls back. So energy levels that are closer to one another, the difference in energy is going to be less, and so it means the photon is going to have less energy. Less energy means a longer wavelength. The bands which appear in the spectra are named after the scientists who discovered them. So with hydrogen, if the excited electrons are falling back to the first energy level, those lines form what's called the Lyman series. And it gives off a series of lines that are all in the ultraviolet region. The next one, the Balmer series, which is found in your data booklet, sees electrons falling to the second energy level. And most of the lines in the Balmer series are coloured, and you can see the colours of those different lines. Then we have the Paschen, Brackett and Thun series, which are falling to the third, fourth and fifth levels respectively, and they all give off light in the infrared region. We reach a principle called the convergence limit. So if we look at this diagram on the right hand side, you can see that as you move out further from the nucleus, that the shells get closer and closer to one another. And eventually they get so close that they converge. And by converge, it means they kind of fuse into one thing. So for example, on the Lyman series, this happens at 91.2 nanometers. The difference in energy between the ground state and the convergence limit is the energy needed for the electron to break away from the atom. So if you're able to give an electron enough energy to go from its ground state to the convergence limit, what you're actually doing is giving that electron enough energy to escape the atom, which would be ionization. So the ionization energy is the energy difference between the ground state and the convergence limit. And the convergence limit is often described as energy level infinity, or N infinity. So the ionization energy can be calculated from the wavelength of the highest energy line in the Lyman series for a hydrogen atom. Now the Lyman series converges at 91.2 nanometers, and so if we use our E equals LHC divided by 1000 multiplied by the wavelength, we get 1312.9 kilojoules per mole, which, if you look in your data booklet, the first ionization of hydrogen is 1312 kilojoules per mole. So we can relate the spectral lines, the emission lines, to ionization data. Now, when we look at these lines, we can look at the wavelengths of light that are absorbed, or we can look at the wavelengths of light that are emitted from an atom. Now, no matter what, it's the same wavelengths of light that are absorbed and emitted by an atom. When we look at an emission spectrum, we are looking at the beams of light or the photons or colors of light that are given off by the sample. This means that we will only see color at these lines and everything else will be black. In an absorption spectrum, what we do is we would see pass white light, which has all the colors, through an atom, and then use a spectrum to spread that light out. As that light spreads out, we form a spectrum that goes from red to purple, and the wavelengths or colors of light that were absorbed by the sample would appear as gaps. And so that's the only difference in appearance between an absorption and an emission spectrum. An emission spectrum is mostly black with a few lines of color. An absorption spectrum is completely colored in the background where you see small black gaps which correspond to the wavelengths that have been absorbed by the sample. Now we're going to look at how this is used in terms of absorption spectroscopy. For absorption spectroscopy, we expose a sample to electromagnetic radiation. And if we're looking at atoms, we need to make sure that our sample is atomized. So it might have been heated up in order to break it apart so that it exists as single atoms. The radiation is absorbed by the atoms and it causes electrons to be promoted to higher energy levels. Any light that is not absorbed just passes through the sample. And the absorption spectrum shows how the intensity of absorption varies with wavelength of the electromagnetic radiation. Emission spectroscopy is a bit different. In emission spectroscopy, you don't give the sample any light to start with. What you do is you heat up the atoms so that they get to high temperature, and that high temperature energy excites the electrons to higher energy levels. As they fall down to lower energy levels, they release photons of different wavelengths. And what happens in this is that you measure the intensity of the light given off at the sample at different wavelengths, and that's the emission spectroscopy. So how do we make use of this? Well, atomic spectroscopy. You can either measure the absorption or the emission spectroscopy for a sample. And each type of atom has characteristic wavelengths at which it absorbs or emits. And the intensity of these wavelengths relates to how many of a type of atom or how much of a type of atom there is in a sample. So you can determine how much of a particular element there is in a sample, even if it is in very tiny amounts. And we're talking about ppb or ppt. That is parts per billion or parts per trillion. And that can be used to check for trace impurities in compounds. Certain companies will label their products with a very tiny amount of particular elements, which allows them to then check that their products are authentic. And it's also a very common type of forensic analysis. In order to do this, in order to turn the intensity of light into a concentration, you need to do a calibration graph. So intensity of absorption or emission is related to concentration. If you do absorption or emission spectroscopy on a set of known samples, you can compare the absorption of an unknown sample to relate it to a concentration. So what you do is you make a set of standard solutions, so solutions with exactly known concentrations, and measure their intensity at a chosen wavelength. You draw a graph of your results, and you should get a straight line. If you then measure the intensity of your sample and then look across on this graph that's called a calibration graph, from the intensity to your line of best fit, and then down, you can relate it to a concentration. So this is what your calibration graph should look like. Nice straight line, intensity on the left-hand side, concentration along the bottom. The units of concentration could be moles per litre, or they could be given in terms of mass per volume, so milligrams per litre. You measure the absorbance intensity of your sample, and then use the line of best fit to determine the concentration. So if this was your intensity, you would read across to your line of best fit, and then read down.